right. Thanks very much for the introduction. Oops. Okay, and thanks. Thank you. Thanks to all of you for attending this session. The key aim of my talk is to present a certain set of theoretical tools that you can use to get some information on quantitative behavior of certain class of probabilistic programs. And the work we did has three main aspects. So first, we aim to compute some lower bound on termination probability of these programs, which we addressed using something that we call stochastic invariants. These sort of reduce the problem to its dual, where we compute some upper bounds on the probability of violating certain assertions, which is a problem for which we introduce concept of repulsing supermartingales. So martingales are certain constructs of probability theory that already have been successfully applied in analyzing probabilistic programs. And what we do is that we somehow extend this martingale-based analysis. And these two contributions are mainly theoretical, but I will also sketch a way of automating this analysis where we can follow mostly standard approaches. So before I will dive into the technical details, let me describe what kind of programs we actually deal with, and I will start from an application point of view. So, of course, probabilistic programs have a multitude of applications, including classical ones like implementing randomized algorithms, or more recent ones like, let's say, reasoning about classical programs that execute on unreliable hardware or with noisy inputs. And of course, there's also use of these programs as probabilistic inference tools, for which one requires these observed statements that are used to reason about conditional probabilities and posterior distributions and so on. So in our work, we focus on the first types of programs without the observed statements, but there is definitely some potential of extending the analysis also to these, and I think this is an interesting aim for future work. Now, to be more concrete, we consider just simple imperative like programs with real and integer valued variables that consist of standard programming constructs, assignments, if-then else branching, while loops, and so on. And in addition, we have two probabilistic constructs, that is probabilistic choice or probabilistic branching, and sampling from probability distributions where we allow both discrete and continuous distributions. And we also allow demonic determinism in both branching and assignments, so that there's some way for abstraction. Now, here we have a short example of such a program, and I will use this as a running example in my talk. So I've, for you to remember it better, I've made up a simple story behind it. So imagine that this models some sort of robot which moves on a line. It starts in some initially non-deterministically chosen distance from the target, and in each iteration of this loop, it tries to move towards the target, but the actual distance traveled is subject to uncertainty, which is represented by this random assignment. And also there is a counter which counts the number of iterations, and if it takes too much time to reach the target, then, let's say, wind starts blowing from the other direction and pushing the robot away from the target. So this is really just a toy example, but sufficient for demonstration purposes. Now, when you are given a program like this, an initial question to ask, which like analog to what you would ask for classical programs, is what is the probability that the program actually terminates? And this is the first aspect that I've mentioned of our work. So there's a quite large body of work aimed at proving almost sure termination of probabilistic programs. But some programs, for example, this one, as one can easily see, do terminate with probability less than 1. So then instead of proving almost termination, what one would like to do is to compute some lower bound on the termination probability. So we want to compute such a number that under each scheduler that resolves non-determinism in the program terminates at least with this probability. And of course, this bound should be somehow informative. It should be as close as possible to the actual termination probability, not like returning 0 for each program or something similarly useless. Well, of course, there was some previous body of work aimed at the reasoning about quantitative properties of this kind of programs, including termination probabilities, for instance, using some sort of logical means. And these are really very powerful, universal tools how to reason about such programs. We take a bit different approach, more algebraic one, that is sort of more aimed to be somehow easily or directly automatable. So what we do is that we take so-called ranking supermartingale technique, which is used to prove almost sure termination, and we adapt it to this quantitative termination using something called stochastic invariants. So before I will present what this new stuff is about, let me recall what these ranking supermartingales are and how they were used. So ranking supermartingale is basically a probabilistic analog of classical ranking function. So formally, it is some function which assigns numbers to program states, and it has to satisfy the following two conditions in each state in which the program is not yet terminated. So first of all, it must be non-negative, and second, it must satisfy some sort of decreasing condition, which states that whenever we are in some concrete states where the function attains some concrete value, the expected value of the function in the next step must be smaller than the current one by some positive, at least by some positive epsilon. So of course, unlike in the classical case, there are now executions along which value of this function might increase, but must decrease on average. If such a ranking supermartingale exists for some program, then this proves that the program terminates to probability 1. We can, for example, take our running example, remove this problematic part, and thus we obtain a simple program which terminated probability 1. And here the termination of this loop is witnessed by a ranking supermartingale, which, let's say, attains value dist plus 3. And it is easy to check that in each iteration of the loop, the value of this function decreases by 1 on average, because minus 1 is the expected value of this sampling. Now, an interesting point here is that for an automated analysis to recognize that this plus 3 is actually a ranking supermartingale, it must know that it satisfies all the required conditions. For example, that it is a non-negative inside loop. So it must know that this is, let's say, at least minus 3. So in other words, the analysis must be supplied with some program invariants in order to deduce the correct supermartingale. And these invariants are also the key for adapting this technique to the quantitative case. So let me return to the original program. Here, of course, this plus 3 is no longer a ranking supermartingale because there are paths through this loop, namely the ones that go through this if branch, along which the value of this function increases, even on average. But a simple thing that we can do is that we can put some additional assertions on some program locations, such that this function satisfies all the supermartingale or the ranking supermartingale conditions in each program states that satisfies these new assertions. For example, here, if time is smaller than 5 times init, then in the next step, this if branch cannot be executed, and thus if we only restrict ourselves to executions that never violate this assertion, then along all such executions, this function basically behaves as a ranking supermartingale. It experiences this average decrease. Now, of course, this additional assertion is no longer a program invariant. There are executions that violate it. But there is surely some upper bound on the probability that this assertion is violated. And hence we called such assertions stochastic invariants. And I think you might now start to recognize how we actually use this stuff. So this leads me to our first sort of simple proof rule, which states that if for a program there exists such an assertion whose probability of violation is at most some p, and at the same time there is a function which satisfies the supermartingale conditions in all states that satisfy this assertion, and possibly also some classical program invariant, then the probability that the program terminates is at least 1 minus the probability of violating this new assertion. So effectively this reduces the quantitative termination to sort of quantitative safety. We now need to bound the probability of violating this assertion. And this is an interesting problem itself. And again, there were previous works that addressed this problem in one form or another. And some distinguishing features of our approach that I will present shortly is that, for instance, we do not require to perform any sort of loop unfoldings. So in particular, we do not need to assume to be working with almost surely terminating programs, which was an assumption in some of these works. And also, we do not require a priori to compute any finite state abstractions of the program. What we do is that we again turn to martingales, and we introduce so-called repulsing supermartingales, which are some sort of dual of ranking supermartingales. And these repulsing supermartingales are inspired by some research in formal methods, where it's inspired by use of these similar martingale techniques in analysis of so-called one-counter Markov processes. These one-counter Markov processes, you can think of them as a sort of a generalized one-dimensional discrete random walk. And what we did is that we lifted the underlying theory in order to apply it to these more general probabilistic programs with possibly continuous variables. So again, the idea is quite simple on the intuitive level. So repulsing supermartingales are dual to ranking ones. In the ranking supermartingales, we seek function which decreases on average somehow towards the set of desired states that we want to reach. While in repulsing supermartingale, we seek a function which is non-negative inside of this set of bad states that we want to avoid. And outside of this set, it has to decrease on average away, so some sort of away from this bad set. So intuitively, existence of such a function testifies that the random execution of the program tends to be pushed, or let's say repulsed, away from this set of states that we want to avoid. So this is a very intuitive argument. For this argument to actually produce something useful, we need to have some additional assumptions about the object, about this repulsing supermartingale. We need a so-called C-bounded assumption, which requires that there is some C such that in each step the value of this repulsing supermartingale changes by at most C. So to be more concrete, the proof rule is as follows. So suppose that we have some program, and in this program some set of states V that we want to avoid. And furthermore, assume that for this set V there exists a repulsing supermartingale with some C-bounded differences, which decreases by some epsilon average. Then the rule says that from each state in which the initial value of the supermartingale is negative, the probability of reaching this bad set V is bounded by this sort of complicated formula which involves these numbers epsilon, C, and the initial value of the supermartingale. So this formula is quite messy, but the point here is that these terms alpha and gamma are always numbers strictly between 0 and 1. So the further away the initial value of the Supermartingale is from 0, the better bound you get here. The correctness of this rule stems from a certain concentration inequality, which is called Osmos Inequality. But I would like to stress that there are other layers above this theoretical core in the proof. It's not just simple application of this inequality. So let's again illustrate this on our running examples. We have the same program with the same stochastic invariant, some program invariants. These are really very simple ones. And if we denote by V the set of states that violate this assertion, then for this set we have a repulsing supermartingale, which looks as follows, again inside the loop, which has differences bounded by 5. So in each step it changes by at most 5, and it decreases by 1 in every step. So we can briefly, to illustrate this, check some of the properties that are required of this repulsing supermartingale. So inside the loop, time increases by 1, and as before, dist decreases by 1 on average, because when we are outside of V, this if branch is never entered. So in total, we have +1, -2, so we have average expected decrease of -1. We should also check, for example, that once we are inside this set V, then the value of this function is non-negative. Again, this is easy. Inside V, time is at least 5 times in it, so these first 2 terms are non-negative. And inside the loop, dist is always at least -2.5, so also these 2 other terms are negative. And in the same way, you could check the C-bound difference condition and the initial negativity condition. And if you apply the proof rule from the previous slide on this repulsing supermartingale, we get that the probability of reaching, the probability of violating this assertion from any of these possible initial state is less than 1%. Now, to conclude, I should just briefly discuss some computational aspects of this, of which the chief one is, of course, how do we actually compute this object, this repulsing supermartingale, for a, let's say, given assertion? Well, as you could have seen, all these ranking and repulsing supermartingale and similar concepts are, from points of view of definitions, very similar to standard ranking functions for classical programs. So we can also use similar methods to synthesize these. So, for instance, what we did in our paper to provide some sort of proof of concept is that we simply restricted to programs with linear expressions, and we were searching only for linear repulsing supermartingales, which can then be done using linear programming like in standard programs. I'm skipping quite a lot of details here. Actually, even computing good probability bounds is a bit more complicated. You can find details in your paper, or of course you can ask me directly. And finally, I should mention that although we were looking mainly for something to prove this bounds on assertion violation probability, these repulsing supermartingales have also other applications. We can use them to refute, for example, almost sure termination or termination with finite expected time, and also to prove so-called persistence properties of non-terminating programs. So to sum up, I've presented some martingale-based techniques that can be obtained to acquire information about quantitative properties of probabilistic programs, like some info on termination probabilities or probabilities of assertion violation. And there is a clear way towards automating these techniques using similar methods as used in ranking function synthesis. And I would like to mention that despite some underlying theoretical complexity, these martingale techniques are, on some conceptual level, simple enough to be easily, I hope, to be easily combinable with other possible tools for quantitative analysis, which I think is a very interesting idea for future work. That's it. Thanks for your attention. I'd like to take your questions. No, we don't have something like this. So it's just if we can compute some reasonable bound, we are happy with that. So in a paper, we experimented on most academic examples, like several generalizations of one and multidimensional random walks, where like the trend can change depending on some conditions in the program. And we obtained bounds of similar or better quality as presented in this running example. And yeah, that was it.
So this probability of termination, is it somehow related also to the expected runtime of the program?
Well, it depends what you mean by related. Definitely, you could also use martingale techniques to reason about this, like about expected runtime. And actually, there were we had some paper on the previous POPL which sort of addressed this, like concentration bounds on expected runtime. So yes, in this sense, the techniques are related. Otherwise, I'm not sure.
It doesn't give you a bound on the expected runtime directly or anything like that.
So for us, I mean, if the program terminates with probability less than 1, then for me, like its expected runtime is infinity because you have positive measure of non-terminating run. Of course, what you could do is that you could condition on the actual run terminating and compute conditional expectation of runtime terminating runs. So based on what I know from this background on this one-counter Markov systems, you'd also use these martingale techniques to somehow reason about this. But it might be a bit subtle, so this is for more in-depth discussion. So, rather simple example, I would try to like say where we expect this to be like applicable. So these martingales are the use of our martingales are based on some sort of concentration bounds. So in principle, when you try to use the repulsing supermartingales to prove that something bad happens with small probability, you're basically somehow expecting actually that this bad thing happens with small probability because you have this vanishing tail bounds on something bad happening. If you have some really very complicated, unpredictable stochastic behavior, then where things might turn out either way. Let's say there is large probability of something happening, and this probability kind of stays persistently large throughout the execution, then this approach would not apply. Also, another limiting factor for the current state is that we require these C-bounded differences. So simply the values can't change a lot if you want somehow to tame this information on the probabilistic execution. Although there is probably some way of at least generalizing this a bit, but yeah, it's for future work.